In this clip, we're going to combine two attributes at seismic resolution to highlight the reservoir. This is the continuation of clip 1, in which relative lambda rho and relative mu rho, shown here in tracks 1 and 2, are cross-plotted and color-coded by the gas volume. These attributes are then rotated relative to the coordinate axis to align the reservoir points along the x-axis. This results in maximizing the energy in the x-axis while minimizing the energy in the y, and giving a better image of the reservoir in the x-axis. The analysis at seismic resolution will include normal incidence and gradient. The attributes in time will be compared with those computed in depth. Next, we are going to QC the attributes at seismic resolution before doing the coordinate rotation. Let's start by looking at the pre-stack synthetic and the attributes generated. Here we have in track 2 the attributes being evaluated, in this case normal incidence and gradient, and in the third track we have the pre-stack synthetic computed from 0 to 45 degrees every 1 degree. The bandwidth used is 5, 12, 50 to 75 Hz. Some observations. Let's start with the attributes in the log plot. We see here the lowest trough does not correspond to the top of the reservoir as we would expect, although the base of the reservoir matches or corresponds to a peak as expected. Let's now take a look at the scatter plot. In the scatter plot, we show the same attributes as in track number 2, and the magenta points correspond to the pay points in the petrophysical evaluation track. When we compare this with the equivalent in depth, we see that the match is not as good as we would expect. And what we're going to be doing in the next part of the exercise is to verifying that the differences in between the attributes in depth and in time are associated to resolution or to tuning, as well as the fact that the trough in the normal incidence does not match with the top of the reservoir. Let's start by doing the QC of the normal incidence trace. For this I have plotted only from 2.08 to 2.14 seconds, displayed only the normal incidence trace in both the attributes and the angle gather track. At this scale we can clearly see the limits associated to the 1 millisecond sampling interval. We see this in both the angle gather and in the sample QC display. To minimize this, I'm going to plot at 1/10 of a millisecond. With this I have minimized that effect in both the angle gather and the sampling QC tracks. The processing in SeisRP is done at 1/10 of a millisecond, and the data can be displayed with as low a limit as 1/10 of a millisecond. At this sampling interval we have an equus frequency of 5000 Hz, and we can create wavelets with as high a frequency as that. So let's start by doing here a display having a wavelet with upper frequencies going from 4000 Hz to 5000 Hz. Create the synthetic data. I'm going to hide the sampling QC track because we're not going to need it. And I am also going to create a plot in depth. I'm going to plot P impedance, S impedance, and density. Here I have also made a zoom going from 3170 to 3270 meters. So we have here in the left the reservoir in time, and in the right the reservoir in depth. Now what we want to verify is that a decrease in impedance corresponds to a negative value or to a red color, and an increase in impedance taking here corresponds to a positive value or to a blue color. So we're going to start doing that. This is a decrease in impedance, the top of the reservoir. It goes to a negative value, red color. This is an increase in impedance, which goes to a positive value or blue color. Again, we have here a decrease in impedance, going to a red color. Decrease in impedance, going to a red color. So we have verified that effectively a decrease in impedance produces a negative reflection, and an increase in impedance produces a positive reflection. Let's now do the same using a frequency of 1000 to 2000 Hz. This would be a decrease in impedance going to a red, increase in impedance still going to a blue, decrease in impedance going to a red. So at 1000 to 2000 Hz we still have the detail in the reservoir. Let's now go to 100 to 150 Hz. And display the synthetic data. This is the top of the reservoir, a decrease in impedance, and we see that effectively it's still a trough, although it's not the lowest value in the trough. This should be an increase in impedance, falls very close to a zero crossing, increase in impedance, falls also close to the zero crossing. So we still have a top and base of the reservoir. This is the base of the reservoir falling close to a positive value, the peak. So we still have the top and the base of the reservoir as negative and positive values, but we have lost the detail within the reservoir. Let's now go to where we started, the frequency that we are taking to be the frequency in the seismic data, 50 to 75 Hz. Create the synthetic. And now we see that the top of the reservoir does not correspond to the lowest value of the trough, although the base of the reservoir does correspond to the peak. So this is the lowest peak, the lowest trough, which does not go to the top of the reservoir. So we have verified, or we have checked, that this in effect is an issue of tuning. And next we'll do something similar or something equivalent in the crossplot domain. Let's start by doing the analysis in crossplot domain by plotting normal incidence and gradient in depth. In this case, we're cross-plotting from 3000 meters to 3062, which is the extent of the log data. Let's now do the equivalent in time domain. In this case, we are using the wavelet of no option, which would be equivalent or more or less the same as a Ormsby wavelet going to the maximum possible frequency of Nyquist given a sampling interval of 1/10 of a millisecond. So here we verify that these are the same, no wavelet and going to Nyquist, and that both cross plots resemble each other in depth and in time. We're now going to start decreasing the frequencies, just like we did in the analysis of the log plots. Let's do 1000 Hz to 2000 Hz. and do the scatter plot again. This would be the scatter plot, and then let's just jump now to the 50 to 75 Hertz that we believe we have in the seismic data, and let's plot this to 1 millisecond, and this is the display that we had been looking at. So what we see here is that this effect that we see at 1 millisecond with 50 to 75 Hertz as the upper end is mostly due to tuning. It doesn't appear when we have higher frequencies or when we remove the wavelet completely. Let's now take a look at the cross plot of relative lambda rho and relative mu rho. We start here with the cross plot in the depth domain, again going from 3000 to 3362, and just like we did with the normal incidence and gradient, we're going to use a new wavelet first to verify that this ties approximately the cross plot in depth, and it does. Now let's change to the Ormsby from 5000 to 5000 Hertz, which would be about the same as having no wavelet. So that's what we have. It matches fairly well with the cross plot in depth. Now let's do the 1000 to 2000 Hertz and plot the scatter plot. That's what we would observe, and then finally what we had originally, which is a sampling interval of 1 millisecond and frequencies of 50 to 75 Hertz. And we do the scatter plot. Now let's move this out of the way and arrange the plots for comparison. So in the upper row we have a cross plot of normal incidence versus gradient in depth and then different frequencies, and in the bottom row we have relative lambda rho against relative mu rho in depth and then different frequencies. We are now going to take this cross plot, relative lambda rho and relative mu rho, and do the coordinate rotation. We are now ready to rotate the data. Let's start with the scatter plot that we just created, and then plot the data in time. So this is the data in time, in two-way time. The second track is relative lambda rho and relative mu rho, the same data that is cross plotted in the scatter plot below. Let's now rotate the data, let's say 130 degrees, create the scatter plot. That produces the effect that we want, which is to align most of the anomaly in the x direction. And let's now do the synthetic data plot. Here it is. Now we see that the energy in the x-axis, the blue line, is highlighting most of the reservoir, and it's interesting to note as well that the zero crossing where the anomaly starts is at the top of the reservoir, and again the zero crossing where the anomaly finishes is at the base of the reservoir. And with this we finalize this tutorial. Thank you.